All right. Hello, friends. Hello. I see people signing on, and I wanted to just welcome you. I also wanted to go ahead and wait a couple minutes as we have people signing on. And as people are signing on, I wanted to tell you a little bit about how this is going to work, and we'll go over a little bit of housekeeping and more about what's going to be happening for us. Now we have a good amount of people going, so I'll go ahead and start going over the housekeeping. And I wanted to tell you a little bit more about how the program's going to run. We have our Getting to Know You, our scientific community, and my name is Kirsty Bourne, and I'm going to be your host. And we have a Q&A section that you're going to see in the very bottom of your screen. And the Q&A section, you can type in the Q&A section a question anytime you have a question, even when our panelist is speaking. And I will save the questions until we have a break time, and then make sure to ask the panelists the questions that you've asked. So that'll be really fun, and it's a great way to interact with our wonderful panelists we have today. I also wanted to let you know that our call is being recorded and will later be put onto YouTube. So if you submit a question, I will not be saying your name, just to be safe for confidentiality reasons. But I do see your question and see it's coming from you. So I just wanted to make sure you knew that I wasn't going to say your name, but we really do appreciate all the questions that you have. And this webinar series is called Getting to Know Your Scientific Community, and it has been created and sponsored by my company, Elim Bio. Elim Bio is busy supporting researchers on the front lines. We are helping with the problem of COVID-19. During this unusual time, we wanted to reach out and feed future scientific curiosity, and we felt the best way to do this is to give you all at home learners a chance to meet some of the really cool scientists within our community. I'm very honored to welcome our special panelist, Dr. Cooksy. Now make sure I said your name correctly, Dr. Cooksy. All right, great. Dr. Cooksy received his BS from Harvard and his PhD in physical chemistry from UC Berkeley. He did postdoctoral research at Harvard Smithsonian Center for Astrophysics. Dr. Cooksy has been a visiting scientist at many well-known institutions, including Oxford and MIT. He is a current professor at San Diego State University. In addition to being a professor, Dr. Cooksy is also an associate director of computational studies, where they study research, free radical structures, and dynamics. And now, what you've all been waiting for, I'd like to highlight our panelists. Welcome, Dr. Cooksy.
Thanks very much. Right, so I'm Andy Cooksy. I'm at San Diego State University when I'm on campus, but probably like a lot of you, I'm stuck at home right now. I did want to thank Kirsty for inviting me to do this, so I could tell you a little bit about the work that we do. And I'm going to see if I can tell you a little bit about with this slideshow. So what I was going to do was try and give you an idea of what we can study in outer space and in traffic and forest fires and a bunch of other things that actually kind of tie them together. It might be the only thing that they really have in common. And I wanted to open with this picture, which was just released recently. This is a picture from the Hubble Space Telescope, which is enjoying its 30th anniversary. So about 30 years ago, at the end of April, it was deployed in space. And then a month or so later, it was actually sending data back to us. So, so happy birthday to the Hubble. And this was one of the pictures that they released. This is a picture from inside the Large Magellanic Cloud, which is a galaxy right next to our galaxy, right next to the Milky Way, where in astronomy, right next to means 160,000 light years away. It's a really cool picture that combines a couple of things going on that are related to what I study. And it begins with this blue ring down in the lower left. This is a picture of a star that's, it's not really exploding, but it's a really bright star, puts out tons of energy, so much energy that it's actually blowing away parts of its own atmosphere. And that's where you see that, why you see that blue ring forming around it. So this star releases enormous amounts of energy, and this is common throughout the galaxy. We have lots of stars that release energy all the time. And some of that energy gets thrown in the direction of this red cloud, which is right next door. The interesting thing from my standpoint is that not all of that energy actually gets through. In fact, an awful lot of it is blocked by this blanket of dust and gas, which kind of surrounds the interior of this big red cloud. The protective blanket means that the gas inside that red cloud is able to get cool enough. It's protected from the energy outside in the rest of the universe. And once the matter in that region starts to get cool enough, it can start to collect, it starts to pull itself together, and it can actually collapse eventually to form new stars. So astronomers are really interested in these regions. They're called star-forming regions. And they start off often very, very cold because you can't have too much heat if you're going to let the matter collapse to form these new stars. Now, I'm a chemist, so what I'm interested in is what the elements are that make up these regions. And there's hydrogen, lots and lots of hydrogen. And then there's some carbon, there's also some oxygen and nitrogen. And these are the elements that we're working with most of the time when we're looking at chemistry in outer space. Now, when things are cold enough, these atoms can come together and form chemical bonds, and that gives us molecules. So molecules are just strings of atoms held by these kind of strong bonds. The interesting thing about molecules in these regions is that they take the little bit of energy that comes in through that protective blanket. They can absorb it, and then they can emit it again. So they can send the energy back out, and a lot of that energy comes out in the form of radio waves. So now we're going to follow those radio waves. They travel long distance, and because they've been emitted by the molecules, they're actually carrying lots of information about these molecules, you know, what the structures are, how the atoms are bonded together. And eventually that information, after a long, long time, reaches us on Earth. After a few 100,000 years, it gets to us, but eventually we get it. And I'm going to blow up this picture here of where that light ends up. We end up seeing these signals in dish antenna like this. This is a collection of radio telescopes in New Mexico called the Very Large Array, a couple of hours outside of Albuquerque. This array actually has, they're celebrating their 40th anniversary this year. And this has been a really amazing observatory for finding out what's going on in our galaxy and in neighboring galaxies, because they can take the information that's coming in these radio waves and process it so we can start learning about the hydrogen, and carbon, and nitrogen, and oxygen atoms that are scattered all over the galaxy, and in particular, what happens when they collapse to form molecules. Now, most of the galaxy is really unfriendly to molecules because there's so much energy being put out by stars like that bright blue star. But in regions where stars form, the temperature again gets cold enough that we can form molecules, and so we can learn a lot about them. And the molecules are especially sensitive to things like the temperature, the abundance of different elements. So we can learn a lot about how the galaxy is put together, and also about how energy moves from one place to another place. And so astronomers use the information about the molecules and the atoms that comes into these telescopes to kind of figure out how they can tell the story of what's going on in a particular part of the sky. Now, The thing that's especially interesting to me, again, because I'm a chemist, is these elements, the hydrogen, the carbon, nitrogen, oxygen. And there's another place that these elements show up, which is in the chemistry of combustion. And combustion is where we burn things, right? Burning is a really interesting chemical process. We take some kind of fuel. Usually it's a hydrocarbon. It's a molecule that's made from carbon atoms and hydrogens. We call them hydrocarbons. And we react them with oxygen. And lots of times the oxygen comes from the air. When that happens, the oxygen forms new bonds with hydrogen and with the carbon that are much stronger than the bonds that we had initially, and that ends up releasing a lot of energy. So combustion is a great way to generate energy if you have a fuel handy. Now, if you're getting the oxygen from the air, there's also a lot of nitrogen in the air, and so the nitrogen often ends up playing a part in the chemistry as well. So most of us don't use rockets like this, but a common place, of course, that you'll see combustion used is in internal combustion engines. So this is how we get cars and buses and trucks to move along the road. We're converting the energy that we can get out of hydrocarbon fuel, much of the time, into the work that's going to drive those wheels around. And this is a great little animation from Wikipedia, where you can see we bring in gasoline fumes in step 1, and then in step 2, they get compressed, and then there's a little spark right there. And that spark is where we have the combustion takes place. And that expands, it pushes the piston down to help drive the wheel, and then we push the gases out and we start the whole thing over again. The thing is, we understand almost everything about how these engines work. We know a lot about the physics, how the heat can be converted to work and how to use the work. What we really don't understand well is what happens at that spark. So right when that reaction happens, that's the fuel combining with oxygen to make new molecules. And that chemistry is really, really complicated. And so a lot of the work that we do to try and build better engines is around trying to understand the chemistry better. Now you might wonder why we would want to spend a lot of time trying to figure out how to burn hydrocarbons. Because of course, when we burn them, we get carbon dioxide, we get nitrous oxides, we get a lot of gases that contribute to climate change. And so I thought if you didn't know already, it might be worth spending just a little time explaining why it's so hard to get away from hydrocarbons. So this is a pie chart just showing that all the energy that we generate in the United States comes from different sources. And you can see there's a big chunk, that green chunk, which comes from renewable sources. We get another chunk from nuclear energy. But just about everything else, petroleum, coal, natural gas, these are forms of hydrocarbons. And so about 80% of the energy that's generated in the country today is from hydrocarbons. And most of that is from fossil fuels. The energy gets used for lots of things, but hydrocarbons in particular have a special application to transportation. About a third of all the fossil fuels that we consume in this country go into transportation. And the reason for that, the reason that it's so hard to move from burning gasoline to using electric cars is because of a property that's called energy density. So energy density is how much energy, how much work can you get out of a particular amount of material. And there's different ways to measure the amount. How much room does it take up? That would be the energy density per unit volume. And how much does it weigh? How much energy do you get out of, say a pound of material? So we want really high energy density. We want to be able to get a lot of energy out of a particular size, and we want to get a lot of energy out of a particular weight. Because especially if you have a vehicle that's going to go wherever you want it to go, you probably have to take the fuel with you. And so you don't want the fuel to take up too much room. You don't want it to weigh too much, because otherwise it's just going to be more fuel you have to burn to carry the fuel with you. Now, there's an important graph in this field that looks like this. It's graphing how much energy you get out of a particular amount of material by space it takes up and by how much it weighs. And so you want your fuel to be like way up in the corner here, so it has a high energy per unit volume, high energy per unit weight. And here's gasoline. Okay, you might think, well, we could do better than that, but this is actually pretty good. Gasoline has a reasonably good energy per volume, pretty good energy per weight. It's also a liquid, which means that it's really easy to handle. You can transfer it easily back and forth. The thing is, what it has to compete with, if we're trying to get away from gasoline in our vehicles, is how much energy can we store? So if we want to use solar power, well, it turns out to be pretty impractical to have solar panels on your car that are going to give you enough energy. And of course, lots of times you want to drive when it's not sunny out. So what we want to do is put that energy into batteries. And here's the problem. That's where batteries are in this graph. They have terrible energy density. And this is why a big area of research now is actually into improving battery technology. We want batteries that can hold a lot of energy, but they have to hold it safely, right? They can't catch on fire. We want to be able to control easily how much energy comes out of the battery. That's something we've learned to do really well with hydrocarbons. We are still kind of working on how to get that amount of energy into a battery. It turns out there are other reasons to study combustion as well, because it happens even when we don't want it to. And so this is a picture from a terrible forest fire, I think in Indonesia, some years ago. And the point I wanted to make is just, if we want to understand the chemistry that goes on here, what kind of molecules are going into the atmosphere when this happens, it turns out a lot of the chemistry is the same. These are the same molecules that I wanted to study when I was looking at what goes on in star-forming regions. And it's because we're still dealing with the same elements: carbon, hydrogen, nitrogen, oxygen. And we have a kind of energetic environment where we can make some of these interesting molecules. We want to know what's going on in the details of this chemistry. So now what my job is to try and understand these molecules, try and understand the chemistry that goes on in these really different environments, in an engine, in the fire, in outer space. And we're asking kind of basic questions about these molecules. How are they shaped? How do you know, when you put them together, you know what atoms maybe go together, but what are the angles? How long are the distances between the atoms? And then if we really want to know the chemistry, we want to know what happens when they run into another molecule. What are they going to turn into? What are the products you're left with when everything is done reacting? And so that's the kind of thing that I try to study. In order to accomplish this, I use two main pieces of technology. I use lasers and I use computers. And I wanted to just show you kind of what the lab looks like. This is actually very much what the lab looks like right now, because there's nobody in my lab, because we're all home. But it does at least give us a chance to see kind of what the instruments look like. And you might notice it doesn't look a lot like a chemistry lab. The work we do is kind of more similar to what happens in physics labs. Here's a quick summary of what some of the equipment is. We have an old laser that we're actually not using anymore that's in this little can over here. This blue box, if you can see it, is the laser that we use now. It's a quantum cascade laser. Beautiful, beautiful piece of technology. It gives us just the kind of laser light we need to study these molecules really precisely. And we have detectors and a bunch of electronics that are needed to control the system. This big long thing that's wrapped in brown wire is the cell where we make the molecules we want to study. The molecules I study are really reactive. I can't just buy them in a bottle because they would turn into something else. So we make them as we study them, and we use high voltage to do that. And so although it's not really like a chemistry lab where you have to worry about spilling stuff, there are other things that we have to be careful about. I've got another lab. This one's a lot simpler design. This is using a different kind of laser. This is called a YAG laser. And if any of you go into research where lasers are being used, there's a good chance this is the kind you'll see. It's a really easy to use, very powerful laser, great for all kinds of applications. And because it is powerful, we do have to be careful. You'll notice one of the things we do in this experiment is we make sure that the laser light coming out of this laser goes into a box where we need to do some work on it. And then it goes into the box where we keep the thing we're going to study. And we try to make sure that that laser light doesn't get out into the lab at all. And so the people who are working on this also have to wear special goggles, and we have to close these curtains to make sure that anybody else in the room isn't going to get hit by the laser. Now, the computers, I'm not going to show you a picture of the computer because it's not that interesting, but I think what we can get out of the computer is really interesting. We're trying to study these chemical reactions, and the way we look at them is kind of like we're walking along a landscape. And this is a really useful way for us to think about how chemical reactions work. If we start over here at this label 2, this, by the way, is one of the molecules that I was showing in that set that we study. If we start over here at number 2, and I think about walking along this landscape to get to another place that corresponds to where molecule 1 is, I can figure out kind of how this reaction is going to behave. If I end up in a really deep valley, that's a reaction that's going to release a lot of energy. If I have to climb over a really tall hill to get to the products from the reactants, that's a reaction that's going to be really slow. Even if it releases a lot of energy, it's not going to happen right away. Whereas if there's only a kind of low hill that I have to climb over, even if it seems to take me more out of the way, I can actually get this reaction to go a lot faster. And so I can figure all these things out about how the chemical reaction is going to progress, how fast it is, how much energy I get out. I can even look at what kind of mixture of different products I might get. Maybe I'm going to get 1, maybe I'm going to get 1C. And I can see all these things if I can use the computer to kind of map out what this reaction looks like. It's an interesting landscape, and it's not that easy to work with because, in fact, I've only shown a couple of directions here, but these are actually landscapes where we have many directions. Every bond distance change, every angle is a different direction on this map. And so it's kind of like, if I want to look at another way of getting from reactants to products, I have to pull out a new map. There's so many directions to travel in that I can't even show them all at the same time. And finally, I just want to wind up showing you that we do some work with other people. I collaborate with a lot of scientists, both at San Diego State and in other places. And this, I just thought was a fun example of work that we've done. This is from a friend of mine in France. His name is Hani Amori. And Hani is a fantastic chemist. He makes these incredible molecules, and then he sends them to me and asks me, well, what do you think? What do you think this is doing? And of course, he already usually knows the answer, but he wants to see if I can come up with the same answer he did. And these things to me are really scary. These are huge molecules. This is a particularly interesting example. He's built a cage, and I'm sorry, you can't quite tell, I realized from this, this perspective, but he's got 4 bars that kind of come down from the top to the bottom. And the idea of this is you can take one molecule and you can lock another molecule inside. And one of the applications of this kind of chemistry, people have been looking for ways to deliver drugs in the body to a particular place. You have a cage like this, and then maybe it opens up and releases the drug only where it's supposed to work so that it doesn't harm other parts of the body. So that's one application of the kind of work we do, is using the computer to try to understand the structures of these really interesting molecules. Much more complicated than the kinds of things I have to study for these combustion reactions and interstellar space reactions. And we also work with some scientists on things like trying to design better solar panel materials that will absorb more of the sunlight so you get more energy out. And other people are actually trying to make materials that will reverse the process of combustion, where instead of generating CO2, you take CO2 out of the air and you convert it back into some kind of solid or liquid form of carbon, so that you can reuse the fuel instead of always coming up with new sources of carbon dioxide to put into the air. Okay, that's just about everything I wanted to show you. Oh, I did want to show you, this is what we did with Hani's molecule. So when we do the calculation, we get kind of a picture of where all the atoms are also that we can compare to the work he's done. Okay, so I wanted to thank, first of all the friends I work with. So I've got pictures of some of my students who have helped me out in the laboratory. Also some of the scientists. This is Hani, by the way, over here. Some of the other people at San Diego State that I've worked with. This is Bill Green at MIT, who I've worked with on some of these problems. And finally, I just wanted to thank you. I know it's hard to listen to somebody for 20 minutes straight, and I appreciate your patience with that. So thanks very much. I'm going to turn it back over to Kirsty.
Oh, thanks so much. Well, we have a couple questions from some students for you. One of them is, how do you take all your lasers to actually make the molecule? Like, what does that process look like for you?
So we actually, we use the lasers to study the molecules. We make the molecules using high voltage. And you know, I should have thought of this. Can I share the screen again?
Yeah,
I can just draw a little picture.
Yeah, you can just hit it again, share screen.
Okay, so let me see if I can get this to work here. So actually what we do, we've got a long tube, and the molecules, again, you know, that we study are kind of reactive, so we can't buy them. But I can take, for example, a couple of gases like carbon monoxide, and this one is called acetylene, and I can put them into the cell. So this big glass tube that was wrapped in brown wire. And then what we do to actually make the molecules, we send high voltage current in the middle of the cell, and it goes through the cell. Let's see, I'm not drawing very well here. It goes through the cell, and as it does that, it busts up these molecules. And so I get chemical reactions to take place that form some of the things I want to study. Like I can put together a couple of the carbons from the C2H2 and the carbon and oxygen from the carbon monoxide, and I can make this HC3O molecule that we want to study. So we actually use high voltage to generate the molecules. And then finally what we do is, as the molecules are being made, we send, I'm sorry, I'm not working at the angle I'm used to, here we go. We send the laser through, and we study how the laser interacts with those molecules. And so that's the role that the lasers play. They actually tell us what the properties of the molecules are after we've made them with the high voltage.
Oh, wow, super cool. Well, one of the students was asking, they were assuming the lasers aren't the same ones that you get at the dollar store. How much are they?
Oh yeah, that's a good question. So, so those two lasers, the quantum cascade laser that I use in the first lab and the AG laser that we use in the second lab, both of those are about $50,000.
Wow.
And so we get money from the federal government. One of those we purchased with money from the National Science Foundation, which is an agency that funds a lot of really basic research into just trying to figure out how things happen without worrying too much about the application down the road. And then we also had some support from the Army Research Office to do some studies on these kinds of reactions as well. And so they help pay for the other laser.
Well, that makes the idea, must do a lot of grant writing then.
So that is right. So writing proposals to explain to the government what kind of research you want to do and why it would be worth providing money for it. That's a big part of our job, as it turns out.
Yeah, cool. We have a very specific question. How much power does it take to make a hydrocarbon 30?
Hydrocarbon 30.
That was a very specific question from one of the students. Maybe just how much power does it take to make a molecule when you're making a molecule? If that's...
Well, so the ones that we're making, which are smaller, I think, than what you're talking about, so we're making hydrocarbons that have like maybe 4 or 5 carbon, oxygen, nitrogen atoms in them. And to make those, we're using about, our voltage is about 2 kilovolts, and it's about 100 milliamps. And so all in all, what is that? I guess we're running, what, about 400 watts? So in the neighborhood of 100 watts. It doesn't take a lot of power because we don't need a whole lot of the molecules. If we can't make too many of them at the same time, because if we do, they start reacting with each other. So we actually have to kind of find the right amount of power to put into the system to get just enough molecules so that we have enough to see, but not so many that they start reacting and forming other stuff.
Okay, cool. We had a couple students that all commented that they loved how you were drawing because they do that to show their math work now at school because they're all doing virtual school. So they thought that was really cool to see that a professor is the same program that they use. So they wanted to just say that was really awesome.
Oh, that's great. I want to say I'm usually better at drawing. I didn't have it at the right angle, but I'm getting a lot of practice now because teaching from home, my class at San Diego State has been going on for the last 5 weeks online. And I'm one of those teachers that I like to draw on the board a lot. And so I had to get one of these so that I could teach from home because I can't do stuff with PowerPoint all the time.
Yeah. Sometimes it's easier to explain when you're actually driving. That's great.
Right.
The kids really liked learning about how the stars are made. They were wondering if you could tell a little bit more about how planets are made.
Well, so first thing I have to do is tell you I'm not the expert in that. And there's a reason I'm in the chemistry department and not in the astronomy department. So I'll just give you my best, off the top of my head understanding. What happens is we get stars with, so as stars start to form, what's happening is you have a lot of gas, a lot of mass that's collapsing under its own gravity. So the material has to come close enough to other material that they all start to pull each other together. And as they do that, there's some net rotation. And it's kind of hard to see when everything is all spread out. But as everything gets collapsed closer and closer, things begin to spin faster and faster. It's like, if you've seen ice skaters, right? When they can spin really slowly with their arms pushed out, and then when they pull them in and they shrink up, they start to spin really fast. And the same process makes this mass, this gas, when it's collapsing into a star, starts to spin really fast. And so you can end up with, instead of just a ball, you get a disk. And the gas that's in the center is where the gravity is exerting the strongest force, and it can pull things together so tightly that you get the nuclear engine started that makes a star ignite. You get fusion reactions. They convert hydrogen to helium, and this releases lots and lots of energy. But the gas that's further out in the disk isn't close enough to become part of that nuclear reaction. And so instead, it starts to cool off, and it can start to collapse into, so again, you have, the mass that's nearby starts to pull itself together, and you get spheres, and they cool down into planets. And depending on where they are in the disk, they can be very different kinds of planets. And so in our solar system, we find that if you go, kind of far away from the sun, we had lots of hydrogen, lots of nitrogen, pretty light elements. And when they collapsed into planets, they didn't make like solid rocks. And so we call those the gas giants, because most of the mass is these really light elements and molecules that don't form ordinary kind of rocky cores. Whereas Venus and the Earth and Mercury, we were closer to the sun, and some of the heavier elements ended up kind of collecting there. And so when the gas in the disk, in this part of the disk, collapsed, pulled itself together under gravity, we got solid planets with rocky exteriors and kind of thin layers of atmosphere around them. So that's kind of my quick explanation for how planets form. I hope it's useful. I hope it's correct.
I think it was great. It was awesome. I mean, I didn't know that, so that was really fun to hear. We had another question. Your lasers are very popular. We have another laser question. One of the students wanted to know if your lasers are high power and what energy source you use when you run them.
So both of these lasers we plug into the wall. So we're using the power plant as our energy source. And the infrared laser, that's the quantum cascade laser, it and I apologize, I don't know offhand how much current it draws. So I don't know how efficiently it converts the energy into laser light. But we get about 150, 200 milliwatts of light out, which doesn't sound like much. And, old incandescent light bulbs, you would buy a 100-watt light bulb to light up a room. And so this is 1,000 times less power than that, almost 10,000 times less power than that. But if you put all that light into a single beam, then there's a lot of energy in that beam, and that's just what we need. The YAG laser, the other lasers, interesting because we're putting energy in all the time, but it's a pulsed laser, and so it puts energy out in like a lot of energy in a really short time. And the amount of time that it spends putting out energy is 100 millionth of a second. So in 100 millionth of a second, it puts out a lot of energy, and then it has to rest for a little while. It rests actually for about 1/10 of a second, and then it puts out energy again. And so that laser, we tend to measure its power instead in terms of how much energy is in a single pulse. The average energy, at least that we're using, works out to about the same, a few hundred milliwatts. The total energy that laser puts out is a few watts. I hope that answers the question.
Yeah, that's the kids study a lot about energy and usage, so that was really great to hear. There was a question which is probably not your expertise, but maybe more of a comment, and wanted to know if you had a comment about it as well. They live in San Diego, and they saw the red tide and the blue light that was coming from the ocean. They were wondering if you had, as a scientist, any comment about that, or that you would like to share.
That's a great question. I wish I could tell you more about it. It's unfortunately one of the things that happened. So I saw the story in the newspaper, and we're so busy on campus right now because we just had finals. I'm sorry, we're about to have finals. We just had our last week of class. I haven't gone back to read the story yet. I know that the algae that are responsible for that have amazing chemistry, and it's true. I don't study that, but we do have chemists. One in particular at San Diego State who studies the biochemistry of microorganisms that live in the ocean, and this is the kind of thing that really fascinates him. So I'm sorry, I can't say more.
Well, I think that's really cool, though, that kids can understand and learn that the bio and chemistry are related. And then there's also things that make them maybe not as closely related. So, we all work together in the scientific field, and sometimes we know the answers, and sometimes we would like to defer to somebody else.
Right. I'm afraid this is one of those times.
Yep. And I do that all the time. I wanted to know a little bit more about what it's like for you to be a professor, because a lot of the students probably have never met a professor. And what does a day look like for you? And what do you spend your time doing besides working in the lab?
So my regular schedule is I usually teach on Monday, Wednesdays, and Fridays, and so I spend a lot of those days getting ready for class and grading. And then Tuesdays and Thursdays I spend just on research, and a lot of that is working with students and meeting with them. I let them do the hard work, I'm afraid, but I'm trying to provide some advice and help them figure out what are the best ways to get the research questions that we have answered. And so we meet with students. If there's a technique that they need to learn, we have a lot of undergraduates. A lot of students who are just there for the 4 years, who do maybe a semester or 2 or 3 semesters in the laboratory. And so they'll come in and they'll need to learn how to do the particular techniques that we use in the laboratory, either on the experiment or in the calculations. And so I'll spend some time with the students just showing them how we do this technique, how we line up the lasers, how we take a problem. So experiments like these, there are all kinds of things that can go wrong because we're putting together all these electronics and the laser and these things that we built ourselves. And so a big part of the research is figuring out when things aren't going the way they're supposed to, where's the problem? And that's a skill that you have to learn. You have to kind of get used to it. So I try and help the students with that. At the same time, I'm practicing my own, ability to identify where problems are. And then we also do some writing. So we have to write grant proposals to ask for funding to keep the research going. We have to write papers to report on the research that we've done. And that kind of writing always takes longer than you think it's going to. I've been doing this for 30 years and I still never remember how hard it is to get one of these things written up. We have to be very careful. We have to really write what we know, not what we think is going to happen. And then we have to be able to back it up. And so just going back through what you've done and finding the evidence to support it is one of the things we spend our time on, just trying to organize, how we're going to make our argument for why this is important or why we think we're interpreting the results correctly. Finally, there's some research that I do on my own, either to help students out on their projects, or sometimes we get every now and then Hani or one of my other collaborators will send me an email and say, I came up with this system and I have just one question about it that I want you to answer. And if they need something fast and I don't have a student with free time to work on it, sometimes I'll do it myself. And so those are usually computational problems. So that's something where I'll work at the computer, I'll build the molecule and try and figure out what the calculation is we can do that will provide us with the property we're trying to explain or predict.
Sounds like you use every area that you studied when you were growing up as a kid. You use your language arts, you use your math.
Right. And, one of the things you learn early on as a professor is how important communication is. And so it really helps a lot if you've had to practice your writing for other things.
Yeah, that's great. Were you always interested in science as a kid, or was this something that you found later in life?
So I was. I'm afraid I can't think of a time when I wasn't interested in doing this. But it was very important to me when I got to college. The first time I started working in a chemistry laboratory. I'd worked in one other in high school, but I was working in a chemistry laboratory, and that was the first time that I heard about chemistry in outer space, that you could actually study how molecules change in these gas clouds that end up turning into stars. And because I've always also loved science fiction, that was brilliant. That was great. And that made me really want to do that kind of work. And that's how I ended up in physical chemistry.
Oh, wow. So did you wear Star Wars clothes on May the 4th be with you? Like the rest of us did?
I go back far enough that actually I'm more a classic Star Trek person myself.
Oh, I love it. How has life changed now with COVID-19 for you?
Right. So I'm not on campus anymore. We had to move our classes off campus about the middle of March. And I had a chance to give class, with people actually showing up in the classroom, and at the same time practice recording the lecture on Zoom. I had one opportunity to do that, and then over the weekend they told us that we weren't going to have any more classes meet on campus. And so right away, everything, all the classwork was on Zoom. And in college, the professors don't teach all day. They can, or at least not every day. We don't teach all day. And so students don't have as many opportunities just to raise their hands and ask us questions. And so we also do office hours. And so I started doing office hours online as well. And I'm lucky because most of my students, they already have their own computers. They're already pretty motivated by the material because the students in my class were all chemistry majors. And so our transition was actually pretty smooth. As soon as I went online, just about everybody was able to join me for the live, Zoom meetings of class. I got my tablet so that I could write as I was writing on the board, but things are much slower. And so we had to say, we're not going to cover this chapter of class because it just takes more time for people to ask questions and get their questions answered. We have to make sure that all the, connections are hooked up and wait for everybody to log in and so on. So, people are definitely not getting quite the education that they would have gotten if we'd been able to stay on campus. But I'm really impressed by how hard my students are working to, let me teach the class the way I would like to have taught it. And so that's been really great. I was really disappointed because this was a class also, the main class I'm teaching. The students were really engaged, asking lots of questions, and moving off campus was going to be really hard. But it's also helped them have the energy, to keep this, to stay connected to the material. So that's been nice.
Did some of your students have to leave San Diego and go to other places where their parents are living?
Yes, so we have at least a couple of my students are from the LA area, and so they're back up there. I think all my students, as far as I know, all my students are in state. But yeah, and we've had students who, they were working part-time to support themselves. If they lost that, then they had to look for other work, and that, perhaps would conflict with the time that we would have class. And so, so it has helped that we've been able to go online and record lectures so that students who aren't able to view, the lecture at the time it's happening can still tune in later.
That is great. I do like that we can record classes. And I know my own students like to go back. They like to be able to rewind,
right,
listen to something they didn't quite understand, where in live you can't do that as much. You mentally maybe. Is there anything else you'd like to share about working at SDSU or your research or your experience as a professor?
Well, I guess I would like to do a little plug for San Diego State.
Yeah.
I really enjoy working there. The chemistry department is a wonderful department, full of people with exciting projects, and we work really well together. And that was one of the things I wanted to get across with that final slide is just we have people who know how to make molecules. We have people who know how to study what's going on at the molecular level in the human body and other organisms. And there's reasons for us to work together all the time because all the sciences are really connected. Just in the research I do, I have astronomy, and it would be nice if I knew more engineering. I don't know that much. And physics and chemistry all kind of come together. And San Diego State is a great place for exploring that because we have great collaborations in the department and with other departments. We work very closely with people in physics and biology and engineering all the time. And it's a nice place if you're from the area and you want a university that kind of understands its relationship to the community. And besides that, I just wanted to thank you all. I do remember my advisor when I was an undergraduate. We had a party for him years later, and at the end of all these presentations, he came up and he just wanted to remind us how lucky we are that we get to work in this field and that we get to explore questions that we're interested in. And it's our whole job really just to ask questions that we find fascinating and then do our best to try and address them. And so if any of you are interested in a career in science, it just doesn't get any better. It's an amazing field to work in, and I hope some of you will keep up with it, and maybe we'll see you.
That's awesome. I love it. Yeah, I love how collaborative, and I love in science how we can ask questions, and it's okay if we don't know the answers right away. Our job is to do what we can to try to solve the problems and solve the questions. I love it.
Right.
Well, I wanted to thank you so much for sharing your time and your knowledge. The students really enjoyed learning from you, as did I. Thank you very much, Dr. Cooksy. And students, next week we have another webinar. It's going to be on Thursday at 1 o'clock, just like it was this week. It's going to be somebody who's studying at Stanford Burnham Prebees, and they're using model organisms to help infants have less heart defects. So that's who we're going to be talking to next week, and more of a biology, chemistry, and we'll go back to another area of science the following week. So we really appreciate your time, and students, stay curious, wash your hands, and keep being kind. Thank you, everyone.
Thank you. Bye-bye.
Bye.